This is Ashley Bedford, founder of the Runtime Diaries, and we are back with another fun LeetCode question for you. This is the hashtag 30 Days of Code Challenge, day 12 with Educative. Let's get into this fun question.
Today we're breaking down one of the cleanest, most elegant subarray problems on LeetCode. Count subarrays with fixed bounds. This video is about taking a confusing brute force idea and turning it into a beautiful O(of)in solution using state tracking and invariants. Let's get into it. Here's the actual challenge. You're given an array of numbers and two special values, min k and max k. Your job is to count how many subarrays have a minimum value equal to min k and a maximum value equal to max k. And here's the critical part. Not at least min k, not at most max k. The actual minimum of the subarray must be exactly min k, and the actual maximum must be exactly max k. Both conditions must be true simultaneously. So if min k is 1 and max k is 5, a valid subarray must have 1 as its smallest number and 5 as its largest number. Nothing smaller than 1, nothing larger than 5, and both 1 and 5 must actually appear in the subarray. And this is where most people immediately get stuck. The instinct is, okay, let me check every possible subarray, compute its minimum and maximum, and test if they match min k and max k. But that approach quickly becomes a disaster. Generating all subarrays takes O(of)n² time. That's already a lot. But then for each subarray, you need to find the minimum and maximum values, which takes O(of)n time in the worst case. So you end up with O(of)n² times O(of)n, which equals O(of)n to the third. And for large arrays, this is completely infeasible. The key is realizing that this is not a brute force problem. It's a constraint problem, and constraints create patterns we can exploit. Once you understand how min k, max k, and invalid values interact, the solution becomes almost trivial. 3 core truths unlock the entire solution. First, any value outside the range min k, max k acts as an instant barrier here. If you encounter a number smaller than min k or larger than max k, any subarray containing that number is automatically invalid. You can't use it. It's like hitting a wall that divides your array into separate regions. Second, a valid subarray must contain at least one occurrence of min k and at least one occurrence of max k. If either is missing, the subarray doesn't meet the requirements. Third, instead of rechecking everything from scratch at every position, we can just track the most recent positions where something important happened. Specifically, we track where we last saw min k, and where we last saw max k, and where we last saw an invalid value. Those 3 observations are how we compress O(of)n² thinking into O(of)1 updates per index. This is the insight that makes the entire problem solvable in linear time. Let's look at a concrete example to see this in action. Say we have nums equal to, from left to right in the array, 1, 3, 5, 2, 7, 5, with min k equal to 1 and max k equal to 5. As we scan from left to right, we maintain 3 pointers. Last_min, which is the most recent index where we saw min k, which is 1 in this case. Last_max, which is the most recent index where we saw max k, which is 5. Last_bad, the most recent index where we saw any value outside the range min k, max k, In this example, that would be 7, since 7 is greater than max k. At each index I, the number of valid subarrays ending at that index is given by this formula. Max of either 0 or min of last underscore min, comma, last underscore max, minus last underscore bad. That formula gives us the count instantly, with no nested loops, no rescanning, and no wasted work. Let me explain why this formula makes sense. Think of the 3 pointers as guardrails that define what's possible. Last underscore min ensures the subarray contains min k. If we haven't seen min k yet, we can't form a valid subarray. Last underscore max ensures the subarray contains max k. Same logic. Last underscore bad ensures the subarray doesn't include any invalid values. Any subarray that includes a number outside the range min k, max k is disqualified. So, when we're standing at position I, the earliest valid left boundary for a subarray ending at I is right after last underscore bad. We can't start the subarray before that because we'd include an invalid value. The latest valid left boundary is the earlier of last underscore min or last underscore max. Why? Because the subarray must contain both min k and max k. So, the latest we can start is at whichever of those two values appear more recently. The count of valid subarrays is literally the distance between those two boundaries. Min of last underscore min and last underscore max minus last underscore bad. If that distance is negative, meaning we haven't established all the constraints yet, we use max of 0 and the equation that we stated before to return 0 instead of a negative count. Here's what the brute force solution would look like in code. This nested loop generates every possible subarray, then checks whether its minimum equals min k and its maximum equals max k. This does work on tiny inputs, but it rescans the same prefixes over and over. That's wasted work. The array never changes, yet we keep recomputing the same information. The fundamental problem with brute force is redundancy. The array never changes, yet brute force keeps checking the same elements again and again, recomputing minimums and maximums that we've already seen. What we need is a way to update what we know based only on the new element we just encountered, without recomputing the entire subarray from scratch. That's exactly what the optimized solution does. Here's the breakthrough idea. If we fix the right boundary at index I, we don't need to try every possible left boundary. We simply count how many left boundaries are valid. This transforms the problem from generate all subarrays to count valid starting positions for each ending position. This is a classic sliding window pattern. We're not actually sliding a window of fixed size. Instead, we're counting how many valid windows end at each position. It's a subtle but powerful shift in perspective. An invariant is a property that stays consistent as we move through the array. At every index I, we maintain three values. Last underscore min, which is the most recent index where we saw min k. Last underscore max, which is the most recent index where we saw max k. And last underscore bad, which is the most recent index where we saw a value outside of the range min k, max k. The number of valid subarrays ending at position I is max of 0 and min of last underscore min and last underscore max minus last underscore bad. This gives us the correct count in constant time per element. No recomputation, no scanning backwards, just update the pointers and apply the formula. Here's the complete algorithm. Initialize last underscore min, last underscore max, and last underscore bad to -1. This represents not seen yet. Initialize ands to 0. For every index I in the array, if nums of I is less than min k or greater than max k, update last underscore bad to I. This value is a barrier. If nums of I equals min k, update last underscore min to I. If nums of I equals max k, update last underscore max to I. Then add max of 0 and min of last underscore min and last underscore max minus last underscore bad to ands. That's it. This is the O of N time and extremely efficient. Let me walk through the logic one more time. Valid subarrays ending at I must start after last underscore bad because we can't include any invalid values. But they also must start no later than min of last underscore min and last underscore max because we need both min k and max k to appear in the subarray. The distance between those 2 points is exactly the number of valid starting positions, which equals the number of valid subarrays ending at I. There are several corner cases to consider. When min k equals max k, the logic still works. A valid subarray must have that single value as both its minimum and maximum. When everything in the array is invalid, the answer stays 0. The formula handles this naturally. When we haven't seen both min k and max k yet, min of last underscore min and last underscore max will be -1. The max of 0 and formula wrapper ensures we return 0 instead of a negative count. Single element arrays work fine if that element is both min k and max k, and min k equals max k, it's valid. Multiple repeats of min k or max k are handled naturally by updating last underscore min and last underscore max as we go. The formula gracefully handles all of these cases without special conditional logic. This solution runs in O of N time. We make exactly one pass through the array, doing constant work at each position. It uses O of 1 space, and we need only 3 integer variables to track positions, plus 1 counter for the answer. This is optimal. There is no way to solve this problem faster than O of N, because you must at least look at every element once to know what's in the array. Remember these 5 things. First, don't brute force subarrays. The number of subarrays grows quadratically, and checking each one is expensive. Second, track state incrementally. Update your knowledge based only on the new information you encounter. Third, maintain 3 pointers, last underscore min, last underscore max, and last underscore bad. These are the only 3 pieces of history you need. Fourth, count valid starting positions for each ending position. This is the mental model that unlocks the solution. Fifth, this is a perfect example of invariant-based thinking. You maintain a consistent property at every step and use it to compute answers efficiently. Master this pattern, and so many other range constraint problems become easy. This same approach appears in problems involving subarrays with specific properties, sliding windows, and state-based counting.
And that's a wrap for this question. We hope that you enjoyed this video. If you enjoyed it, like it down below, share it, send it to a friend who might need it. We thank you so much, and we will see you again next time. Bye.